Welcome back. I'm Ebony, teacher at BIAC, and soon you'll meet Oki, my assistant for today's lesson. Most of you have heard of the hot topics like global warming and climate change, but how many of you have heard of ocean acidification? Ocean acidification refers to a decrease in the pH of our ocean over an extended period of time, primarily caused by the uptake of carbon dioxide from the atmosphere. It has serious consequences for marine ecosystems and biodiversity in Australian waters. So what does this mean?
G'day team, I'm Oki the Octopus, and I'm here today to talk a bit about ocean acidification and to fight for my mates who are out there in the ocean finding it tough with all this extra CO2 coming into our atmosphere. I'm hoping that you'll be able to help me.
Let's go through our lesson objectives. First up, our what. What are we learning today? Today we are learning to understand what is causing the ocean to become more acidic, to identify which marine organisms are affected by this, to understand how the pH of water changes when carbon dioxide is added to it, and to identify current threats to our ocean's ecosystem. So why are we learning this today? We are learning this to understand why ocean acidification is occurring and how we can reduce our own impact. So how will you know that you have been successful as a learner at the end of this lesson? Success at the end of this lesson looks like this. You will be able to describe the process of ocean acidification, explain which marine organisms are affected and how, explain how carbon dioxide changes the pH of seawater, and propose solutions to reduce the amount of carbon dioxide levels that you are responsible for emitting. Ocean acidification is called the silent killer, as there is a silent struggle occurring in our sea every day. Oceans cover approximately 70% of our Earth's surface and contain about 50 to 80% of the world's life form. Up to 3 billion people rely on the ocean for food and livelihood.
It's you humans, you're the problem. The cars, the factories, the power plants, the aeroplanes, the way you're living your life, that's the problem. And what you need to realise is, if you're the problem, you're also part of the solution.
Since the Industrial Revolution, levels of carbon dioxide in the atmosphere have continued to increase due to human activities. Emissions from our transportation, factories, power plants, burning of fossil fuels for electricity, aeroplanes, human respiration, and deforestation all contribute to the rising levels of carbon dioxide in our atmosphere. Our ocean has the incredible ability to be able to absorb approximately a third of the carbon dioxide that is being emitted into the atmosphere. This is approximately 30%, which equates to 22 million tonnes of carbon dioxide per day. It dissolves and reacts with the water. At the surface of the ocean, you can see carbonic acid exists. This is responsible for the increase in acidity of our ocean. You can see it's responsible for two things: the increase in hydrogen ions as well as the decrease in carbonate. Let's talk about the hydrogen ions and what effect this has on pH. So what makes pH high or low? So it's our hydrogen ions that have the power to determine how acidic or how alkaline our solution is. As you can see on the left, we've got lots of hydrogen ions, which can be represented by the H+. The more hydrogen ions we have, the lower the pH. And on the right, there's only one little hydrogen ion. So the lack of hydrogen ions, or a low hydrogen ion concentration, indicates a high pH. So what is pH and what impact does pH have? Well, as you can see, our pH scale ranges from 0 to 14, with our acids at the top and our bases or our alkalines at the bottom, and our neutral in the middle. pH is what they call a logarithmic scale, which means it's not linear. So for every number that you head up towards 0, for example, between 4 and 3, means that there is a 10 times more higher increase in the acidity than what there was at 4. Same thing if you head down the scale between, just say, 10 and 11. Number 11 is 10 times more alkaline than number 10. Let's explore pH in experiment number 1. Okay, we've got experiment number 1 called the bubbly cup. So what equipment do we need for experiment number 1? You can see I've got my safety goggles on, I've got a pair of gloves on, a lab coat to protect my clothing, and for the actual experiment we need a straw, we need 2 clear glasses that you can clearly see through, some bromethanol blue solution, something to measure your bromethanol blue solution with, and some seawater. The other thing that I've brought along for this experiment today is our pH scale. Now I've spoken a little bit about pH prior, but you'll see here that pH is actually sitting at approximately the pH range of 8. You'll notice that as I put our indicator solution into our pH, into our salt water. So let's do that. So we've got 200 mils of salt water measured out into each glass. And what I'm going to do is we're going to measure 1.5 mils of bromethanol blue solution to tell us the approximate pH of that salt water. Once we know the approximate pH of that salt water, I'm going to blow my expired carbon dioxide out of my mouth through the straw into one of these glasses. And hopefully what you might see is a colour change. So when we're looking at our pH scale, the carbon dioxide from my expired breath will hopefully reduce the pH of the salt water. Now what we'll be looking for to see a reduction in pH is for our colour to go from a bluey colour more towards a green. So keep an eye out to see if you can pick up on that pH change. Okay, so opening up our bromethyl blue solution, we're going to measure 1.5 mils into each of these. Oh. That's 1.5 mils into the first cup. And 1.5 into the second. We're just going to give those a little swoosh around so that it combines with the salt water and gives us the same colour. So you can see now it's giving us that nice bluey colour. That's indicative of that pH of approximately 8. Now I'm going to pick up my straw now, and what I'm going to do with the straw is, as I explained earlier, I'm going to blow my expired carbon dioxide from my breath into one of these glasses. The reason I'm not going to blow into both of the glasses is I want you to be able to see what the colour started as and what it finished as, so you've got a comparison. Or in science we call that a control. So let's go about approximately 1 minute and we'll see if we can get a colour change. you go, that's only about 30 seconds and we can already see a distinct colour change between our original saltwater solution, which approximately was a pH of 8. Let's have a look and see what we can categorise this one as now. So if we're looking at our colours, we're trying to match up which best colour fits our new solution. So we've gone from approximately an 8 and we're heading up the scale to about a 6 or a 7 by matching the colours to our solution. How incredible that CO2 can make such a difference to pH in a solution. Next up is experiment number 2, exploring the effect of carbon dioxide in the atmosphere. Okay, so the next experiment that we have for you today is called carbon dioxide in our atmosphere. So what materials do we need today? Once again, you can see I'm wearing my safety goggles, my gloves on, and I've got my lab coat. The equipment that we will be using is we've already made up some bromethanol blue solution, which you can already see in our 2 cups presented in front of me. We're going to be using some bicarb soda, a half a teaspoon and a full teaspoon. I've cut some little paper cups down to that size. That's going to indicate our atmosphere. We've got some lids for our cups. We've got some vinegar, and we've also got our little carbon dioxide producers, or one of the carbon dioxide producers that we have in our world that contribute to our higher levels of carbon dioxide. So our first step is going to be to put together our atmosphere. So we've got our seawater that you can see in front of you with its beautiful pH demonstrating about the pH of 8. Inside this cup, what I'm going to do is put half a teaspoon of bicarb soda, and then I'm going to attach the cups to the plastic cups that you can see in front. So let's get half a teaspoon of bicarb in each of these. Okay, we're just going to sit them inside the cup about 1 centimetre below the surface and then tape them there, making sure that the cup that we've inserted is not touching the liquid that's already in the seawater liquid. So that's our bicarb soda set up ready to go. In order for us to produce our carbon dioxide, we actually need to be able to add something to this bicarb soda that's going to react and produce carbon dioxide. So we've got the perfect ingredient here, which is our white vinegar. Just like I did with the bubbling water experiment, we're going to keep one as our control and then one as our experiment. So today this one's going to be our experiment and this one's going to be our control. So in a moment I'm going to put 1 teaspoon of white vinegar into the small paper cup, making sure I don't spill any vinegar into the seawater because that will really quickly change the pH of that seawater. I'm then going to put a lid on top of my cup and we're going to observe for a couple of minutes to see what happens. What we're hoping will happen is that the vinegar will react with the bicarb soda and it will produce carbon dioxide. And that carbon dioxide will circulate within the cup and eventually will start to make its way down to the seawater and start to diffuse into that seawater. And when carbon dioxide diffuses into the seawater, you'll notice that it will actually start to change colour because it means it's changing the pH of that seawater. So let's see if we're on the money and if we're correct. So just taking that lid back off. We're not going to put any vinegar into this one because this one is our control. We don't want a chemical reaction to occur there. We don't want to be producing any carbon dioxide. So I'm just going to pop the lid on for our control. Okay, so that's 1 teaspoon or approximately 5 millilitres of vinegar straight into our little cup, lid on as quickly as I can. And we're going to leave that for a couple of minutes and see what reactions we can, what colour change may occur. As you can see, with our controlled experiment, we still have a blue seawater indicating about a pH of 8. Now that we've had our chemical reaction between our bicarb and vinegar take place, the colour of the seawater has changed dramatically. And I would like to call it maybe a light green colour, which indicates a really significant change in our pH of that seawater. So what was causing this? What was causing this was the chemical reaction producing carbon dioxide. And as that carbon dioxide dissolved into the seawater, it then increased the amount of hydrogen ions in that seawater, which lowers the pH, hence the colour change indicated by our bromethyl blue solution. And our last experiment for today is our dry ice experiment. So what do we need for this experiment? Once again, our safety equipment, as you can see that I'm wearing. We've got a pair of tongs to help us pick up our dry ice. We've got a beaker which is full of bromethyl blue solution dispersed in seawater once again, indicating our pH of 8. And in this esky I have our dry ice, which is actually frozen carbon dioxide. So what we're going to do is we're going to see what happens when we put dry ice or frozen carbon dioxide into our seawater sample. So have a think about it. What prediction would you like to make? What's going to happen to our seawater? What's going to be our reaction as a result of this experiment? Let's find out. So using our tongs, we're just going to drop a little bit of our dry ice into our sample and see what occurs. As you can see already, we have a drastic change in our pH of our seawater. Likening the pH of our seawater to approximately a pH of 2 at the moment, which is similar to a lemon. What a cool reaction. As you can see, the carbon dioxide gas is also trying to escape as this reaction is occurring. So not only is carbonic acid causing an increase in hydrogen ions in our salt water, but it's also causing a decrease in our carbonate. Now, the less carbonate we have available, the less shells that marine creatures can produce, as well as our corals, as these are the building blocks for their shells and their skeletons.
Ebony, I mentioned earlier, I'm here to fight for my mates. Because my mates, some of these marine creatures, including clams, oysters, snails and urchins, I'm losing these guys at a rapid rate. These guys find it hard to build their shells and spend more of their energy trying to do this than searching for food, so their numbers are starting to dwindle.
There are many different organisms that are directly affected by ocean acidification. These organisms are all calcifiers, animals or algae that use calcium carbonate to create their internal structure. As seawater becomes more acidic, carbonate becomes less available. This means that these calcifiers don't have the building blocks to create their shells or skeletons. Imagine what that would be like for a snail if it couldn't make its thick shell. If the ocean becomes more acidic, then shells might even begin to dissolve.
And what about coral? Have you thought of them? Coral coral polyps, those tiny creatures that build our magnificent reefs. Our reefs being our most productive ecosystem in the ocean. When corals stop growing their hard exoskeletons, the reef stops growing or will start to shrink. Scientists already propose that ocean acidification could wipe out corals by 2050. And what about the fish? Scientists have conducted research and have exposed fish to high acidic environments. And fish that are exposed to high acidic environments become lost, they become anxious, and they have a harder time finding food and detecting predators, which ultimately, eventually leads to their death. You've already met one of my mates, Planky, the zooplankton. They have very thin exoskeletons, and the increased acidity threatens to react with the calcium carbonate of their shells. They form the basis of our marine food chain, and without them, the food chain would collapse.
What is happening to my exoskeleton?
So, Oki, I'm sure that there's something that we can do to help. What are your suggestions to help us clean up our act?
Oh, I'm glad you've asked, Ebony. There's plenty these kids can be doing. Get on your bike and walk to school or take the bus. Be smart with your electricity. Unplug your devices, turn off your lights and your fans when they're not in use. Don't buy fast fashion. Choose locally handmade garments or participate in clothing swaps with family and friends. Plant a garden. Plants absorb CO2, so get planting. Avoid processed and packaged foods. Our processing plants are our major polluters. Eat local, wherever possible, in season, so we aren't emitting CO2 transporting foods from elsewhere. And dry your clothes on the clothesline. One dryer load uses 5 times more electricity than washing them. We have the perfect weather to naturally dry our clothes. Hang them out. Our actions and choices ultimately make a difference, and we all share the responsibility to do whatever we can to address this issue, big or small.
So, what can you do to reduce your carbon footprint? Let's revisit our success criteria to see how you went today. Can you describe the process of ocean acidification? Can you explain which marine organisms are affected and how? Can you explain how CO2 changes the pH of seawater? And can you propose solutions to reduce the amount of carbon dioxide levels that you are responsible for emitting? Australian curriculum links are listed here, which includes the learning area of science and our cross-curricular area of sustainability.